Good morning, good evening, good afternoon, and welcome everybody. So today we're going to be talking about piecewise and step functions. This is lesson 3.7. We skipped a couple lessons in here that we're actually going to be covering later down the road. So we went from 3.4 to 3.7. So please don't freak out if all of a sudden you're like, where's 3.5 and 3.6? 3.5 we're pushing down the road, and 3.6 we're actually going to do in a month or two when we cover geometric sequences. So in this lesson, ladies and gentlemen, we didn't quite start the bell work. We will again in chapter 4, which will begin the following week on the 17th of September. So we have been able to identify and graph linear, some exponential, but we really haven't messed with quadratic functions yet, but that's okay. We're going to be able to identify some step functions and some piecewise functions. On your notes, ladies and gentlemen, you have this vocabulary. Please do the annotated notes. So circle, step function, piecewise function, and greatest integer function, and then underline the important characteristics of those as well. Step functions, we're not going to deal too much with these today. I'm going to show you a cool thing on Desmos that will help us with the only 2 examples I gave you, but I wanted to make sure you guys saw what this graph looked like. This is an introductory to the open and closed intervals that you guys should have learned last year, but as we move forward, we'll do again. And the closed interval means that is like the equal to, and the open interval means it's on that number, but it's not actually equal to. You remember the greater than or equal to sub. So let's begin. Your first one, graph this function, f of x equals x minus 2. So here is a cool thing. If you guys actually Google what's called a step function, Desmos has this awesome little thing here set up that gives you what's called a floor. In this function, or you could type it up, y equals a. They have that for the value that sits outside. So a actually is going to equal 1, because remember, what is f of x? And then if it says equals x, well, what's in front of the x that we don't tell you anymore because you're in high school now? It's a 1. So we're going to start with 1 on here. H is 0, this function, and then the function k is 0. Ladies and gentlemen, HK form. We will be talking a lot as we get into quadratics about h and k. Okay, what the HK form is, how you make transformations about it, and then what we're going to do. So in our example, it says if you were to graph it, it'd be x minus 2. So I'm going to take this h and watch the graph as I move it to the functionality of 2. So when I do x minus 2, did you see what happened? It shifted it to the right 2. How about that? That's pretty cool, huh? So if I were to have you guys graph the function of this, I didn't put any on your notes. One thing I want to make sure is that x minus 2, you would actually do what? Minus 2, if I were to change it again, it actually vertically, it moves to the right 2 units. Okay, so you're going, oops, I got it at 0.9. So it moves to, you guys can see how the integers now moved 2 units over, and you would have a circle here, open interval here, and a closed. So if you were to state the domain of this, remember the domain is all x values. Even though, for on this, the domain, even though this is a closed and this would be an open interval, I can't draw it on this board anymore. I took that functionality away of doing the external stuff. But imagine, if you will, a closed solid circle here, open interval here, closed, open, open. Your domain is actually going to be all real numbers. Now your range, though, is going to be what? It's actually all integers. That's in that little box that's right above you. And all integers are all whole numbers, actually, as well, including negatives. So 0, 1, 2, 3. But it cannot be the spaces in between. Imagine if you take a step. Okay? You're just counting the flat surfaces as you go up. The next example here. Let me change this back. If you guys look at your notes. 0. Oops. 0. Thing. All right, nice. All right, if you guys look at your notes right here, the next one basically says, all right, so let's try this again, ladies and gentlemen. If you see a funky cut right there, it's because my video stopped recording. And thank you, iPhone 6, for being beautiful. All right, so what we're going to do is our functionality. Let's move on to this function, okay? Where if we look at our notes, it says 2 now, and 2 times x, okay? So we're going to graph this. So what we're going to do is we're going to go back to our original equation. If you guys remember what we did here, okay, this is the original setup of the floor. So what we're going to do is change the value in front of it. So on your notes, please make sure you guys actually write this section down, because if you can write this down, then what it'll do is it'll help you later on. You can play around with this, try to see how everything moves and understand what the h and the k functionality does. So in this example here, I'm going to change this to, let me take the slider, and it says I'm going to times it by 2. So you guys can watch the graph as I change it. Watch how the expand out. And so now you guys can see what happened. Is it went from 1 to 1 step to now it moved, and the interval in between is now what? It's 2. So imagine if I moved it to 3 in front of it. It would actually move up to 3, 4, 5. You guys get the setup. The step function will actually spread out the more you multiply it by. I thought, ladies and gentlemen, looking at that kind of stuff is cool. Hopefully you guys see the same thing, and then you understand the concept, okay? We'll move on, but just understand that that's kind of what we're looking at. The domain and range of both of these are the same. The domain is all real numbers, and the range is just all integers or whole numbers, including the negatives, okay? Okay, next, a piecewise defined function. This is pretty interesting when we start doing this. Hopefully you guys understand the process and concept behind it. And if you don't, rewatch this video real quick. I have to go fast through it, as fast as I can, but hopefully you guys will get the gist. All right, remember this function, if you guys look at this, you're probably saying, what is this? Well, f of x, okay, if you guys remember, f of x basically means y equals, okay? These two functions are the same. But what I'm looking for here is I'm looking for what is f of x is negative x. So f of x, if you guys remember, the parent function was just basically would come out like this, and that's f of x, okay? You keep drawing a line, it looks nice and pretty. F of negative x is actually a -1 in front of the slope. So your slope is what? -1. So we know that a -1 slope is going to kind of come out like this. It's going to start, sorry my line is crooked, I'm just trying to make sure I get it on the dots. And so this is your graph of a negative x. But what I want is I want a restriction. Okay? I don't want the whole graph of negative x. I want it only if x is less than 0. So I want the functionality to be x is less than 0. On your coordinates, 0, 1, 2, 3, 4, you guys get it? 0, -1, -2, -3. What values are less than 0? Well, it is what? Everything that comes up and leads to 0. Now, if you guys remember last year, hopefully you guys did this, greater than or equals to. On a number line, when it was greater than or equal to, or less than and equal to, you had what was called a closed interval, okay? And if it was not equal to it, it was open. Because what did it actually mean? It meant your interval is going to go up to that number, but it's never actually going to equal that number. And so how we represent it in the graph, if it is not equal to, we would actually start this graph with an open interval. Now, what is the functionality of x minus 2? On Desmos, ladies and gentlemen, I want you to write this down, please. You can actually graph these out. Remember, f of x, you don't have to start with y or f of x in Desmos, but you put negative x. If you hit the, when you guys are doing this, either on your keyboard or if you're doing this by hand, if you hit the A-B button, it gives you up your keyboard with all your letters. Here's the bracket you need to use. It's the little funky one that I can never draw, that it looks like a bird kind of, or a weird face, something. I just can never draw that. When I draw it, it looks like a freaky dude. What you want to do is, you put that bracket in there, negative x, the bracket x is less than 0. Let me turn it on. Look at what it does. Creates the graph, but what does it do? Same thing I just represented. Now your next graph is negative x plus 2. A transformation which we kind of skipped over, and we'll cover more transformations later. is basically what I'm doing is I'm taking this graph, okay, and I'm going to move it. And I'll show you how you do that on Desmos. Same thing, negative x plus 2, and then you have your interval. If I turn that on, here's your graph for that. Now the reason it goes every interval, so I want every value that is greater of x that is greater than 0. So your interval is going to start on this line. If I were to draw these lines straight out, what did I do? I moved the negative x line. I actually moved it up 2 spots. So I could actually connect this red line. If I moved it up, I could connect the red and the blue lines together. Matter of fact, if I do it on my notepad here, watch it, plus 2, look at that. Same thing, okay? Now let me restrict it back. Check that out. Okay, so it's basically the same line. I'm just moving it up 2, and I'm closing the interval. On your graph, ladies and gentlemen, on your notes, it's an equal to. So it means your interval needs to be closed, and then you would draw it down, and you would keep going, okay, to infinity and beyond. So what is the domain of this function? The domain is all real numbers, left to right, because it does equal 0, and the range is all real numbers. Okay, so D equals all real. Whoa, that's funny. I was wanting to do that. The domain is all real numbers, and the range equals all real numbers. Not aha, that should be all. All right, next on your notes, ladies and gentlemen, you guys, hopefully you wrote the bracket down on how I did it. You try it on Desmos, please. All right, ladies and gentlemen, hopefully you tried to graph this on Desmos, 2x plus 1, and then basically f of x equals 3. So let's see what that looks like, shall we? All right, so let me turn these 2 off. 2x plus 1, every x integer is greater than 0. So it starts here, goes up, and then I just put 3 with the value. Now you can put y equals 3. You have a straight line. So that's a little crazier and pretty cool, actually. I think it's cool. You guys may not. But, so the value starts at, let me do that again. Well, actually, I know the function of a slope-intercept form is y equals mx plus b. So I know my intercept is going to be at 1. And that's an open interval, okay, because it is not equal to, and it's going to be plus 2, so it's actually up 2 over 1. So do I need to look at my graph again? No, I do not, because I know how to do the slope. Y equals 3, and with a closed interval, okay, y equals 3, 1, 2, 3, closed interval, and it's every value that is less than x, and it goes that way. That's pretty cool. What is the domain and range? This is more difficult. The domain on this one, ladies and gentlemen, left to right is what? All real numbers. Domain is all real numbers. But what is the range? Okay, your range, what's the bottom number we start with? Well, the range is actually going to be, the bottom number is 1, but is it equal to it? No. So the range is actually going to be less than y. That, ladies and gentlemen, is your range. Start at 1, but we can't equal 1. That is every value greater than 1. Okay. Now on the domain here, if you wanted to do negative infinity to x, actually I'm not supposed to do the equal sign. I heard I get yelled at for that. So let me this. So that would be another way to write your domain. Ladies and gentlemen, we'll go over this again on your homework. You'll have a couple of these, and I want to make sure you guys can do the domain just like this, so please make sure you make an annotation of that. And if the range is all infinite numbers, and then this, ladies and gentlemen, and I'm not supposed to do that. So it's just y is less, or 1 is less than y, which is less than infinity. Okay, that is the range. Okay, next, real-world functionality. Models a hiker's distance in miles from the start of a trail X after she begins hiking. Graph the function and then interpret each piece of the function. When I wrote this out, I was like, oh, this is going to be weird. But ladies and gentlemen, I thought it was really cool. Okay, when you do it on Desmos, piece by piece, the first functionality is 3x. And then 3x, and you put your little restriction on. You can see it starts Here it moves up. The next one is 3. Look at that. Moves over just a little bit. And then your final piece is 2x. And it goes up. So the functionality of this, when I saw it, I think this is pretty cool because you could draw a picture on here. Create a cool graph. I know last year Mr. Slant did it in his class for Algebra 1, and I know this is a cool activity, so did Ms. Dubell, that we might actually incorporate later on in the year, because using this model, you guys could draw a picture, but using linear equations. So what does each function mean? Well, what it means is that 3x, okay, the rate of change, if I got rid of all this stuff, it's going to be 3x plus 0, so where does she actually start the hiking at? Well, she starts the hiking at 0, and she's walking at a rate of change of what? 3. So she's actually walking about 3 miles per hour in the first hour that she hikes. And then the second piece, if you guys go back to this, what happens is she starts walking 3 miles per hour because you're going from 0 up 1 over 3, 0 to 3, so she's walking 3 miles per hour. Then this hiker takes a half-hour break, doesn't move, time passes, and then she's chilling like a villain right here. And then after a half hour, she what? Takes off again, and her rate of change would be 1 up, 2 over. Now, I know it's hard to see, but if I drop this graph down a little bit more, you can see an intersection here, and what is my rate of change? 2 up over 1, so my rate of change would be 2. So she slowed down, went from 3 miles per hour, stopped for a half hour, started walking again, and went 2 miles per hour. That's pretty cool, I think. That's what the functionality is. So, ladies and gentlemen, here's what it is. I'll walk out so you can write this down. And here's the final piece. All right. Now, one key aspect that they have on this graph that I forgot to talk about is she walked the first mile, mile and a half to here, and then the rest of the constant would be 2. Now, does it say she ever stopped? No. If we wanted to see a functionality, say she stopped after 5 hours, you could put a restriction on the Desmos piecewise function right here. Instead of 2x is infinity, you could actually put a restriction on this to 5, and knowing after 5 hours you'd be able to see how far she walked. You have a cool bar graph to go along with it. Final piece of the puzzle, ladies and gentlemen, is you guys try this guided practice. All right, this is an equation representing somebody working at a job. When I look at this equation, I see 8x. So, Javon, probably, he makes $8 an hour. So the functionality of earnings you'd be able to put on a graphing calculator is from 0 to 40 hours because that's a typical hour job. But after 40 hours, he gets time and a half. Okay, and it's represented by this equation. Time and a half is actually, it doubles your salary. Okay, so imagine time and a half is called doubling your salary. So if you make $8 an hour, you would double the salary, which is 16, but then cut that down. It's an hour and a half. So it's not a full 16. It'd be, what is 8 divided by 2? It's 4. So time and a half would be 8 plus 4. So he now would make $12 an hour. That's one cool thing sometimes about hourly employees. So your functionality, if you were to graph it, would be 8x. Your restriction would be to 40. Then your next graph would be 12x minus 40. So I can't see that because I got to go out to 40. Got to go farther than that. So what you guys can see is my functionality starts to change. And it looks like on this graph, at 40 hours, Giovanni makes $320. And then guess what happens? I can't go any higher. It actually stops me. The function does when I'm tracing the line. So the maximum value he can actually make in a 40-hour period is $320. That's the information we're looking for. And then after that, for every hour he works, he would actually gain, and his salary would do what? It would actually increase. So if Javon worked 47 hours in a week, he actually would make what? $404. This is kind of a cool functionality. If you were an hourly employee, you could figure out your own wages using these two linear equations and this restriction. So ladies and gentlemen, please understand that. Graph the function, then interpret each piece. Each piece. The functionality is the range on this would be from 0 to 320 like we talked about. And then after that, ladies and gentlemen, it would be to infinity and beyond. Hopefully you guys learned something. Hopefully you guys can graph this. I put kind of a little thing on there. This is kind of an interesting lesson we worked on in class. We'll have an exit ticket most likely. The homework will be in the comment section. And if you're watching this on Canvas, it should be listed right there on the events. Ladies and gentlemen, I hope you have a great night, and I will see you, or day, whenever you're watching this, and I'll see you in class next time.